Hello, everybody. You are welcome to clip 6 in the part 2, which is related to principles of digital communication in the course of modern wireless communication and applications. This is actually the last clip in this series of part 2, and here we talk a little bit more about block and convolutional codes. So usually when we say block code, we mean that we have the information bits and also the parity or the check bits like together within the same like data packet or within the same code channel code. So we have the message bits and check bits together. If the message bits is distinguished from the check bits, we call this code as systematic block code. Otherwise, it is unsystematic block code. But remember now that we have the message bits that we have, and also we add there to the parity or the check bits to that block, but it is not distributed over other messages. Okay, this what is done by convolutional codes. So the convolutional codes is not depending only on the current message bits, but also on the previous bits. It depends on the memory. There's a memory in convolutional codes, so the code itself and also the message are distributed over longer time. Okay, this has some benefits actually, like for example maybe for space-time coding, for puncturing for the code, and it has some other benefits. However, as a performance, of course it is still depending on the Hamming distance and also on code rate and so on. Of course, we have other kinds of coding. For example, for the linear block code, we have linear codes and non-linear block code. Also, for the convolutional codes, we have different kinds of different realization of the convolutional codes. We have the turbo codes, where we have series of convolutional codes like in parallel, for example, and we have interleaver between them. We have like soft encoder or hard encoders. So we have different kinds of encoders. So coding topic is very wide topic in digital communication. It has many different algorithms, and it has reached to very advanced levels already. So, for example, with very small signal to noise ratio or EB over N0, with using this kind of convolutional codes, we can reach to very good accuracy or very good performance, as it is known from channel limit that we need EB over N0 to be zero point 0.7 at least in order to detect the message correctly. And with these turbo codes, for example, we are quite close to that limits. Again, we mentioned about this Hamming distance before, and the Hamming distance, we said this is the distance between the valid codes, and we keep the Hamming distance between valid codes as large as possible. But of course, to increase the Hamming distance, the minimum Hamming distance means that we need to use larger number of parity check bits, which means that we can reduce the code rate, and then we might get problems with the throughput. So most like some resources are allocated for bits not related to the original message itself or to the throughput. Uh, for linear codes, the good thing with linear codes that the minimum Hamming distance is just the minimum weight of the code. Remember that the weight of the code is the number of ones in the binary. So the number of ones is the weight of the code. So for linear coding, that you don't need to compare your between each two code and computing the minimum, because this can be, especially for long codes, can be it might require like huge computation resources. However, that for linear codes, it is enough just to check the minimum weight of that code, and this will be the weight or the minimum Hamming distance in that code. Of course, without all zero codes is not included in that computation. There is a relation actually between Hamming distance and the capability of block codes. So you can see here, for example, if you want to detect up to U errors, bare word or bare word is the total code, including the message bits and also the parity bits. So bare word, for example, if we have seven bits and we want to be able to detect only detection without correction, u bit. So the minimum distance should be or must be actually greater than or equal to u plus 1. For example, if you want to detect only one error, bare word, then the minimum distance you should design your encoder or coding that to have a minimum distance, Hamming distance of 1 plus 1 is 2. Okay, and if you want to correct up to t errors per word, then the minimum distance should be at least 2t plus 1. For example, if you want to detect and correct, for example, one error, then the minimum Hamming distance must be 3. So 2 times 1 plus 1 is 3. Okay, and if you want to guarantee that you want to detect t errors and correct u, which is greater than t errors per word, then the minimum distance should be u plus t plus 1. For example, if you want your code to be able to correct one error, but it should at least detect 3 errors. Okay, in that case, the minimum Hamming distance must be 3 plus 1 is 4 plus 1, 5. So the minimum Hamming distance must be 5 in order to be able to detect U errors and correct one error. So this is a general like rules how to select the minimum Hamming distance inside your like word compared with the capability of detection and correction. Actually, we mentioned in the previous clip how it works, but now with this figure we can also explain it a little bit more. So for example, as we mentioned that we add when we add parity bits to the code, the space of that code becomes larger, but we have only few which are valid and the others are invalid. Assume now we have only those 4 valid codes, and in the same time the total number of possible codes, here we have like 1 2 3 4 5 6 7 8 9 10 11 12. So we have, of course it can be more, but just for explanation, we assume that we have 12 possible that words. However, only 4 of them are valid block, the others are invalid. Okay, now assume that you send this valid block, that this was transmitted. Okay, this was transmitted in the receiver side. Because of interference, because of noise, because of fading, as we will see in the next part when we talk about more about channels. So there was one bit block error. One in that block, in this block, there is one error happened. One bit was in error. Okay, so it depends on that error where it happened. So it can, for example, move to this invalid block, or it can be this invalid block. Okay, and now we can see that we receive this invalid block. We know at the receiver that this block is invalid. Okay, what we can do, we can start measure the distance, the Hamming distance between this received block with other valid blocks. So now we know that our capability or our coding capability is able to correct only one error. So the only valid block which has Hamming distance of only one is this one. So based on that, we can correct the error and have the valid block. So this is the correction capability. Okay. Um, because you can see from this block, the Hamming distance to the other valid block is 2. The Hamming distance from this block to this one is even more because it will be 1, 2, 3, 4, 5, and so on. So the closest one, or the one which has only one Hamming distance, is only this valid block. Then we can correct this error. You may ask, what if two errors happen in that block? As we mentioned in the previous clip, we said that it is much less likely that we have two errors in one block than to have one error. So for example, if the probability of having one error in this block is, let's say, 0.01 1 per percent, then the probability of having two errors in the same block, it can be 1 per 10,000, or one even less, like 1 per 100,000, for example. Okay, now if assumed, but it happened, yeah, even it is very less likely, but it happened, it could happen. So if the error was two errors in this valid block, then what we will receive this invalid or this invalid. Okay, now we have two errors, so this block was received this one or maybe this one. Okay, and assume that we receive this one. So the error here is detected because we were able to detect that it is invalid. But because our decoder is implemented to correct one error, so they didn't know that there were two errors. Okay, what will happen? They will check the distance again. So the distance from to this valid block is 2, to this valid block is 1. So they will decide that the transmitted block was this one. However, this is error. There is a mistake. And but this is the coding, because our coding is based on detecting two errors but correcting only one error. Then it will make a mistake in that detection. However, the probability of such mistake or such error is very small, is very small. If the error, as I said, if the error is for one bit is 10 of the power, for example, -2, then the probability of having two errors will be 10 of the power -4 related to, not equal, but related to. It is more, it depends on the number of bits per block. Okay. um, Let us ask other question. If you send, for example, this valid code, not two but three errors happen. Once because of three errors happen, then this valid code will be received as another valid code. So it will come here, for example, or here. In this case, uh, our decoder will not see any error. It will think that the transmitted one was already this code. However, it was this one. Because of three errors, now we say that those three errors are undetectable. So this pattern is undetectable. So it cannot be detected by by our decoder. So it will be received as a valid code. And this, of course, will be a problem. Okay, so as we have more more sophisticated decoder, as we will be able to detect and correct more errors. Let us take a numerical example to explain those concepts. Now we consider that we have two information bits, 00011011. Those, of course, coming from our source. For example, we have our source here. Maybe we take the simple example of the microphone, for example, that we have voice. Then we have analog to digital converter. then it gives us series of bits, number 0, 1, 0, 0, 1, 1, 0, 1, and so on. Now we take the information bits like 2 by 2. So we take, for example, 0, 1, and we take 0, 0, 1, 1, and so on. But we don't send them directly, so we have that, for example, 1, 0, and we added the check parity 0, 1, 1. So those three bits are check parity or check bits or parity bits actually. So they are not they don't carry the original message, but they have been added to protect or to increase the reliability of the transmission. Okay, now out of those 2 bits, the total number of combination that we can obtain is 4, as you can see. However, after increasing those parity bits, we add 3, so the total number is 5. Then the total number of possible combination is 2 of the power 5, and this equal to 32 possible combinations. Out of those 32, we have only 4 valid combinations. Okay, you may ask how in what order or how could we add these bits? Actually, we have some like techniques, very simple techniques, but there is no time or to talk about them in this fast review of digital communication. But we have already several simple techniques in order to generate how to find those bits. And remember that uh, the criteria of adding those bits to make the valid words as far away from each other as possible, as in the previous example that we saw, like this way. So we don't make this valid block and we add the second valid block here, for example. In this case, this will not work. This will be very bad encoder in this case. Okay, so but anyhow, let us take it as it is now. So we have 5 bits, which means that we have 32 possible combinations. Only 4 of them are the valid blocks. Okay, now we let us see that from the previous slide that we have seen, those are the only 4 valid or permitted code words. Okay, now if you this is linear code, and the minimum distance, as we mentioned, the minimum Hamming distance of this code depends on the minimum number of weights for the smallest word except the all zeros. So in this case, we have 3. So the minimum distance of this code is 3. As we mentioned before, that Hamming distance of 3 is able to detect and correct 1 error, and actually to detect 2 errors, but maybe not all combinations that it can be detected for the 2 errors. However, that it is able for sure that to correct one error. Okay, and let us assume that we receive this code word 00110. Compare this to the permitted code. It is not one of them. So your receiver, your decoder, will know directly that this one is invalid. So they will decide, or they know that there is error happened already in the transmission. Is it possible to correct the error or not? Simply they will compare it with the all possible or permitted code word or valid code words. So now by comparing them, so you can see the distance between this one and all 0 is 2. The Hamming distance between this one and the second word is 1. The Hamming distance between this one and this one is 1, 2, 3. And also the Hamming distance with the third one is, you can see that 1, 1, yes, and 2, 3. So it will be also 3. So the Hamming distance is 1 only with this code, which means that the bit which was in error is the second bit. So it was 0, 1. Here it was 0, 0. So they will correct this error. So all what they do is only correcting this error. As mentioned before, if this one actually due to two errors, okay, it might be detected but cannot be corrected, as we will see it in the next slide. So you can see here, for example, if we receive the code 01001, and if you measure the distance between this received code with all four permitted codes, you will find that this code will have a minimum distance 2, but with two codes. It can be 2 with this one and this one. Which one was transmitted? We don't know. We cannot decide because it has the same Hamming distance with two different codes. In that case, we detect the error, but we cannot correct the error. Of course, it can be, for example, this one with 50% and this one with 50%. So maybe you say that I will select any one of them. Oh, okay, you can do that and taking the risk of making this decision. There's another method for the decoding, is because this decoding is based on it's just called hard decoder. So because actually we don't receive the signal as exactly 0 and 1, we will receive some soft value. For example, if the signal is between 0 volt up to 1 volt, for example, then we can have like threshold if the signal is equally likely, and we say that any signal less than zero point 0.5 is 0 and any signal more than 0.5 is 1. This is called like a hard decoder. However, we can improve the decoding process by using soft decoder. In the soft decoder, we keep every signal, like for example, normalize it from 0 to 1, but it is as it was received. For example, if we don't receive like 01001, but assume that we receive like point 1 and 0.9, for example, and point 4, okay, and let's say point oh 01 and point 0.7, okay, instead of 01001. Now, after the hard decoder, of course, they will make this like 0 and will make this 1 and this will be 0 and so on. However, the probability that point 0.01 to be 0 is higher than the probability of point 0.1 of point 0.4 to be 0. However, in the threshold or in the hard decoder, they will treat them in the same manner. It will be both this 0 and this is 0 because this one is less than 0.5, so it will put it as 0. Okay, so in the soft decoding, instead of hard decoding, we will measure the distance based on the real values that we receive. So in that case, we can have like more accurate decoding process. Actually, this can increase the decoding reliability or the decoding performance by 3 dB by using soft decoding instead of hard decoding. Okay, now we come to the convolutional coding. The convolutional coding, as we said, it has also memory. So we don't send like packet by packet as we did before, that we take 2 bits and then we add some parity bits and that's it. Okay. Now we like uh, we have memory. So the transmission of bits is distributed over time. Okay, and in that case, in the convolutional code, by the way, it is also linear coding. It is defined by three parameters. Is n is the number of bits or the total number of words, and k is the information bits. It is the same actually in this way like block code, but now we add k capital. K capital is the number of like buffers or memory cells inside the convolutional code. Usually we use the previous k minus 1 bits in the process. Let us take example to see. For example, this one. Now this is our input bits. You can see, so we have the input bit, it will be stored in this memory, but this is the state. Actually, the state is the previous bits. For example, assume that we have 1 0 1 0 1 1 0. This is the data. So the first time 1 will arrive to this input state, but usually we start with the 0 0 state, so we will have in the beginning here 0 and 0. But in the next clock, of course, we compute now the output bits, how it will be. But in the next clock, this one will be shifted here. So it will come here 1, and this 0 will be shifted to the other side. So it will be like here. So now we moved actually the state from 0 0 to state 1 0 because the input is 1. Okay. And of course, the second input here will be 0. And then we can compute the output. So the output, you can see that for every one input, we have two outputs. What it means that n equal to 2 and k small equal to 1. So in this coding, in this example, the coding rate is equal to 1 divided by 2, so it is half. But it has memory k equal to 3, the total states. However, the memory is k minus 1 is equal to 2. This is the state, the order of the state. Okay, you can see now that depends on the input bits, the states will be moved accordingly. For example, if now we said that this is 1, we move from state 0 0 to state 1 0. The next bit is 0, which means that 0 will come here, and as we said, and the third bit is 1, so which means that the 0, the previous 0, will go to this state, and this one will move to this state. So that now the next state is 0 1. Okay, and every time we compute the 2 bits at the outcome. So now what we have the output bits, and we have also the state movement, the movement of the state. You can see now that depends on the input bits. The output is not depending only on the input bits, but depends also on the 2 previous bits. So it is distributed in time. So if there is a truncation in the data with certain like percentage, we could also still able to retrieve the information bit with some degradation. And also we can use this like distribution in the especially when we have the states with much more numbers for the previous, then we can use them like in it is called space-time coding, as we will describe them later when we talk about like MIMO antennas. Um, okay, so if we check the states, how the states are moving, so we can see here the finite state machine. So this is the states actually of the convolutional code. So it was like 0 0 as we showed before. If the input is 0, actually it will move to the state 0 0. You can see it. So if we have here, let me just erase this. Yeah. So if we have already 0 0 in the beginning, 0 and 0, and the input here is 0, when the input is 0, next step or the next clock, this 0 will be moving here, and this 0 will be moving here, but the state is still at 0 0. If the input is 1, at the next click, this one will move here, so we will go to the 1 0. So this could be easily represented in this finite state machine. As you can see that from 0 0, if the input is 0, it will again goes to 0 0, but if the input is 1, then we go to the state 1 0 as described. And if you go to the same block, you can see that the output will be 1 1. And if you are in state B and the input is 0, you will go to the state 0 1. If the input is 1, it will go to state 1 1, and so on. So based on this finite state machine or the movement machine, how the states are moving, okay, this describes that we have valid movements based on the inputs. So based on the inputs, the states, for example, if you are in state A and the input was 0, it will repeat to state A. If the input is 1, it will go to state B. If we found that from state A we jump to state C, this is impossible according to this uh, 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 diagram, or according to this encoder. This is not possible to move from A to C. But if during the decoding we found that we move from state A to state C, it means that there is error happening during the transmission. So because this is not allowed. From A, either it was 0 or 1, we can go from A to A or from A to B. So if we move to other states from A to C or to D, it means that there is error happening during that transmission. Okay, how to correct this error? The correction of this error depending on of course it is NP problem, but there is very easy to implement algorithm. It's called a Viterbi algorithm that it can be used to find the minimum distance allowed movement, as we can see here. So it is called a Trails diagram. In Trails diagram, what we did simply is that we move or we expand this state into time domain. Okay, let us see how it works. So now this is state A, which means that we have 0, 0. State B is 1, 0. State C 0, 1, and state D 1, 1. This is the states, the inputs of those states. Always we start with state A with 0, 0. Now you can see if the input is 0, we will move to state A, and you can see always we are moving to state A, from state A to state A once it is 0. If it is 1, then the output will be 1, 1, but we will move to state B. Okay, from state B, you can of course confirm this going back to the state machine. From state B, it can go to state C if the input is 0, and if the input is 1, will go to state D. From state D, it will go to state C if the input is 0, and will go to state D if the input is 1, and so on. So this is the ideal trace diagram. Okay, now we check. We know that the first two inputs must be 0, 0. Okay, and those are the first outcomes. So now, if we are in state A, and then the first 2 bits were 1, 1, it means that it was moving to state B. Okay, from state B, the second two states should be 1, 0 or 0, 1. What happened if the second one, after 1, 1, the second bits were like 0, 0? 1, 1 in the beginning, and then it comes 0, 0. 0, 0, it means that from state B, okay, is not possible to go, because it is not possible to have 0, 0. We have either 1, 0 or 0, 0, 1. 0, 0, okay, is not allowed in this trace diagram. Then by taking these steps, like step by step, and unless we complete the certain number of states in time, we can compute the minimum distance to see to which path it should take in order to correct those errors. Okay. So the channel coding, as we mentioned, that it is very important, extremely important in all digital communication systems. Most of like 3G, 4G, and modern wireless communication, they use what is known as turbo codes, which can give much higher performance than convention the basic block or convolutional codes. But the major concept is similar, but here we use also interleavers. We will talk about interleavers and the space-time coding in the next part. So, coding methods have greatly improved the performance of digital communication by providing the possibility of detecting and correcting errors, and again, all digital communication systems using some kind of channel coding. Now, after this part of convolutional code, we have covered the major things that we need to know about digital communication, and of course, next part we will talk about channels and also radio communication, like when we talk about antennas, MIMO antennas, and some like multiple access methods. What we mean by CDMA, what we mean by off DMA. Those are the major like modulation techniques applied in wireless communication nowadays. So all these things will be like described in some details in the coming parts. Thank you for this. So this is now we conclude the part two of this course, and let us now just revise the outcomes that we got from this course. Okay, so if you have already watched all these 6 clips with reasonable care, and also attending the online sessions, and if you solve the quizzes successfully, so it means that if some problems were not, or some quizzes were not clear, so you can come back to the slides and to the lectures to understand them. So if those things went fine, so you should be able now to demonstrate the concepts of digital communication. Digital communication concept should be now clear in your mind. You should be able to explain the major difference between analog and digital communication. And now you are aware about sampling theorem, what we mean by sampling in time, and also the quantification and analog digital converter, digital analog converter. Those things should be clear also. Now you should be able to demonstrate the different digital communication schemes and their performance. So when we talk about amplitude shift keying, or for example frequency shift keying, or phase shift keying, or QAM, why this is preferred, what is the meaning of spectrum efficiency, what is the meaning in terms of performance, in terms of probability of error. Those things now you should be clear for you. And also you should be able to explain in detail the concepts of digital receivers. When we say that correlator receiver, now it should be clear what we mean by correlator receiver, and also the impact of noise, the fundamental and different kinds of coding. So now you know what we mean by block code, what we mean by convolutional code, and how coding, channel coding is working, and also the concept of source coding, encryption for decryption, and for compression, for example. So those concepts should be clear. Um, as I mentioned before, digital communication is wide area, so it cannot be covered even in one complete course. Now we try to cover it in like 2 lectures, but not everything, of course. But the major structure of digital communication, it should be clear for you. So that's all about this part, and now we have done with the yes with the part two of digital communication, and see you in part three. Thanks a lot.